Okay, thanks. Okay. So let me tell you what is the problem we're going to discuss today. So here is the problem. We are given a system of linear equations over reals. So a linear equation over reals will be of the following form. We have some coefficient, real coefficient rj1 times xj1. J is the index of the equation plus rj2 xj2 plus rj3 xj3. And this is supposed to be equal 0. Okay? So we have homogeneous equations over 3 variables each. There are real coefficients to the variables. What else? Okay, I'll denote each equation by EQ usually. Okay, and we have a bunch of them. Okay, the variables assume real values. Okay, so a system like this, a homogeneous system, can always be satisfied just by the all zero assignment. So what we'll ask is for a non-trivial assignment. Find a non-trivial assignment that satisfies as many equations as possible. But we're going to have a twist. And the twist is that we'll say, okay, we're walking over reals. We'll be very happy even if we don't have exact satisfaction, if we manage to have this sum equal 0.00001, whatever. If it's approximately 0, this is also fine with us. Okay, so there will be some parameter which will say gamma. What is the absolute value of the left-hand side with which we're going to be happy? Okay, so this is the new problem. You're given a system of approximate or system of linear equations, and you want to approximately satisfy them. What can you say? Okay. So let me tell you. So I said that we want to rule out trivial assignments. Let me tell you. Wait here. Okay. Let me give you some formal definitions and what is our non-trivial. Okay, so we'll ask the assignment to have norm 1, which means that if we pick a random variable, so I'm going to assume some regularity here. Each variable appears in the same number of equations, or has the same probability to occur in an equation. The sum of squares should equal 1, so I have this normalization. I will also ask only for assignments that are bounded. So I'll have some parameter b, and all the xi's should be at most b. Okay. And now, yes, thanks. And the task is going to be have as much norm as possible on equations that are satisfied, that are approximately satisfied. So we would like to maximize over the equations. So this will be an indicator to whether the equation is satisfied with margin gamma. And we would like to count the contribution of the satisfaction of this equation by the norm on the equation, where the norm on the equation is going to be, we just pick an x from the equation, and it's x squared. Okay.
This square is the sum of squares or addition of squares of these 3 variables that appear there.
Yes, exactly. Okay. So I want to satisfy, I want to have as much norm, the total norm is 1, I want to have as much of it on satisfied equations. So let's see that this indeed avoids the problems with the all zero assignment or the approximately zero assignment and so on. So if I have an all zero assignment, this will always be 0, and I got nothing. If this will be almost always essentially 0.
What do you mean? The all zero assignments cannot have norm 1, so you rule out the norm 1?
Yes, okay. Maybe I have the all zero assignment where one variable has, or just a few variables have some.
B is not very small.
What?
B is not very small, so it doesn't force everything to be basically the same norm.
Yes. You can, for now, you can think of B as some constant, say. Okay. Later we'll pick B, which is larger, but it's small. No, but you could have some of the variables completely 0, and then some other variables that are B. But then in all those equations where you only have zeros, and thus they are trivially satisfied, you will have 0 contribution. Okay. Fine. So this is the problem that we are looking at.
Is it related to some smooth version where you do something like e to the minus the equation or something like that time?
What if I replace this by something else?
No, replace the indicator by something like, I don't know, say e to the minus the equation or something.
It's hard for me to say how this will behave. I don't know. Okay. Fine. So this is the definition, and let me tell you what is the theorem we're proving. So we show the following for any delta bigger than 0. Suppose that you're an algorithm and you're given a system like this. Given a system of equations where you can satisfy almost everything when 1 minus delta fraction. Oh, wait, of equations can be exactly satisfied.
Satisfied with the high norm, or
Exactly satisfied.
no,
What?
No, but you count the norms of the variables when you satisfy.
With variables plus
Okay.
minus 1 or what?
With an assignment that satisfies with an assignment, with a legal assignment that satisfies these.
Yeah, this, but in the satisfaction you don't count. It's not like the task. Satisfying 1 minus delta fraction may be satisfied with very low norm.
Okay, well the equations, okay. And even with the assignment, which is Gaussian. Which with an assignment that is really well distributed and you don't have
So why don't
normal.
you say why? So you have the task to maximize its parameter, right? This parameter.
Okay.
So why don't you say that the system satisfies it with some big parameter? I guess the conclusion that you can't efficiently do it with some small parameter. But so why is the assumption different than the task?
I want to say that it's even I'm given something even stronger than this.
Look if you don't
I'll,
say something about
no,
the sign.
if I say
What does
this,
it mean Gaussian? I'm not sure what I mean by what it means.
it means that if you pick x according to a Gaussian distribution, or
I mean, it's a fixed assignment, but it's just once. It's not distribution.
okay, let's Let's have something
so
else.
Is this Gaussian?
Let's- Let's write exactly the expression that we had before.
So you want to say something like this?
The
This
equation
and more
is
something
essentially
That's
zero.
okay, yeah. That's good. Yeah, the assumption looks.
If this is at least 1 minus delta.
Okay.
Okay. It is NP-hard. To find an assignment, with norm 1 and bounded, well, so now I'm going to let the algorithm have very large margin. So the margin that I'm going to let it is going to be something of the magnitude of square root delta, say 10 to the minus 4 square root delta times the norm on the equation. So there is an assignment that satisfies essentially everything, almost everything with zero margin. Now I let the margin be much bigger, and I also don't ask for 1 minus delta, but only say 0.99. Okay. So I give you this constant fraction of norm that you can play around with. And also I let you play with the margins, and it's going to be NP-hard to find this even given this assumption. Okay?
What is B?
What?
How will B be?
B will be, say, log 1 over delta. It's not going to be very essential for the talk.
But also the assumption has these x's are below b. That's both for the assumption and the conclusion.
Okay. Fine. So this is our theorem.
Just to make sure, with some caveat.
With some caveat, there is one actually little asterisk that I should put. That this is not zero, but this is going to be arbitrarily small and independent of anything else.
That's a minor caveat. There is somewhat little more significant caveat, which is this. You can do it only for these simplified argument. You have these blocks and.
No, but we can. We don't really need this assumption. Okay. Okay. No. So this is not going to be zero. Huh? I should say that before this we reported just hardness result based on the unique games conjecture, and we now think that we have NP hardness result. What Subhash says is that right now it's only written up for some simplified setting, but it should hold for the general setting. Right? We know how to do that. Okay. Fine. This is the result.
This might be the first time that someone converted the unique games hardness result into an NP hardness result, right?
start by
Yes.
looking your Hardness and report it.
Yes. No, so I want to tell you why this result is interesting. Or so the question is, what are those parameters that we see here? Why the square root delta? And what I want to say is that this result is tight, and not only it's tight. There is a semi-definite programming-based algorithm that achieves essentially something almost as good as what we show is hard. Okay, so let me show you the semi-definite program you can write for this problem. So there is a very natural semi-definite program that just comes from taking each variable xi and replacing it with a vector vi. And now that you have this, you can say, I want to minimize the margin. I want to minimize the margin square, the expectation over the equations of rj1, vj1 plus rj2, vj2 plus rj3, vj3, the two norm of this vector, and subject to having norm having norm 1 and having bounded vi at most b for all I. Okay, so this is a semi-definite program, a natural one. If we look at what is given, yes. So I even wanted to say the stronger condition. So we're basically given that this is at most delta. So there is the minimum is at most delta. The semi-definite solving the semi-definite program will allow you to find a vector solution that achieves that. You can take the vector solution, round it in the standard way by projecting it into Gaussians. You'll mostly have the boundness condition satisfied. You can just throw away or just replace by zeros when this is not satisfied. You can arrange this to be 1. This doesn't affect the result too much. So you'll get this. You'll get a real solution with this equals essentially delta. The square will be essentially delta. Yes, and thus the expected margin will be square root delta. And with high probability, you can have the margin at most, say 10 to the 4 square root delta. Okay, probability 0.999. The margin will be at least 10 to the 4 square root delta.
Yeah, and it will only be a constant probability. You cannot push this to 1, the probability, in a way that will depend on delta. The algorithm wouldn't give something. You write 0.999. I'm just wondering if the algorithm you described would not give actually.
The algorithm that I described can give the expected margin. The expected margin squared will be essentially delta. Okay. So there is a trade-off between
Yeah, so the
probability
trade-off is
and
between
the
constant
and the constant
margin
here.
and this. Okay, very good.
Okay?
Yeah.
And up to what exactly is the constant here, our result is tight. Okay, it matches the semi-definite program based algorithm. Okay. Good. Okay. So I should say that the reason that we got interested in this problem and we proved all those things is that we were interested in pursuing the unique games conjecture. And so we have this program, so I don't know. So we have this program for the unique games conjecture, which we're not sure will actually bring to the proof of the conjecture. But this is the motivation of our research. And the program says, okay, first, prove NP hardness. For this problem, this thrilling over the rails. Then deduce that there is NP hardness for tooling over the rails. And from this deduce the unique games conjecture. Well, this is what we have, and this is this theorem that I'm going to talk about. The question is whether we'll be able to take this result and pull from it a result for linear equations where each equation depends on two variables over the real. So research started with this candidate reduction from 3-lin to 2-lin. We now know that there are counterexamples to this reduction, and somewhat hopeful that we'll be able to fix it and get this. And such a result will essentially be the spirit of the unique games conjecture and should imply the full unique games conjecture. So this is essentially the program.
No, proof of the 2 implies 3. Yeah.
There is no proof of the 3 implies 2.
No, number 2, not 2 linear. You have numbers 1, 2, 3.
So okay.
The second
What we do
implies the
have.
third result.
Okay.
Is it-
What we do have is that if we manage to get such a result for 2-lin with a constant soundness here, then we do get the full unique games conjecture. We still don't know whether it makes sense to expect here some constant soundness. Okay. Fine.
Could you give some intuition why sort of 3-lin to 2-lin is nicer in the case of reals as opposed to finite fields?
Okay. Yes. So there is this intuition that over finite fields, the 3-lin problem and the 2-lin problem are completely different in their behavior. So over GF2, we know for 3-lin, we know NP hardness. This is the Hastad famous result, where in the completeness, you can satisfy 1 minus delta, be consistent of the equations, while in the soundness case, you will only be able to satisfy half plus epsilon. Okay. On the other hand, for 2-lin, we have an algorithm. So this is a hardness result. And for 2-lin, we have an algorithm, or for max cut. We have an algorithm that can distinguish between essentially 1 minus delta and 1 minus square root delta. The question is, what is the constant here? Okay, so the behavior is very different. Over the reals, this doesn't happen. So over the reals, well, as we saw just now, if we consider the expected margin, then even if in the 3-lin case, there is an algorithm that gives expected margin of 1 minus square root delta. Okay, so if you consider the expected margin squared, or the expected margin, then both 3-lin and 2-lin, we expect this square root delta. Okay, so over the reals, those problems are, at least quantitatively, similar. Of course, there is a big difference between showing that an equation on 3 variables to show a result with equations on 3 variables and showing a result with equations on 2 variables. This is indeed the big question here. Okay. Good. So let's start. So I want to talk about this. So my plan for this talk is to only show a dictator test for 3-lin over the reals, and not show the entire NP hardness result. I do want to remark that the NP hardness result incurs a blow-up in the size. The blow-up in the size is, there is an exponent which is polynomial in 1 over delta. Delta is the completeness. So there might be a sub-exponential algorithm already for 3-lin over the reals. Okay. So let's skip this. So the first step in designing NP hardness or UGC hardness or those reductions is typically to show a dictator test. In the language of the problem, so here it's a dictator test over reals. So let me tell you what this means. Suppose that we have a function f from Rn to R, and we know that f is bounded and has norm 1. And what we are looking for is this tester or distinguisher, where the tester is going to get query access to f, where f is from one of 2 types. Type 1 is f is a dictator, where this means that f of x just the value of x in one specific coordinate I. So this is one option that the tester may get. And the other option is that maybe f is far from dictator. And what exactly far from dictator means, I'll tell you in a minute. So the tester is either given access to a function like this or to a function that is very far from having this structure. And what it's supposed to do is to pick some equation over three variables. So an equation of the form R1, Rj1, f of x, j1, plus Rj2, f of x, j2, plus Rj3, f of x, j3.
These x's are now
equals. Now x's are in R to them. Okay? So it picks 3 inputs to the function. It queries the function on those 3 inputs, 3 points. It performs a linear equation, an homogeneous linear equation over the values that it got. So this is in the language of the problem that we're interested in. And now it checks whether this is 0 or this is far from 0. If it's 0, it's essentially 0. It's supposed to say, yes, the function is the dictator. If this is far from 0, it's going to say, no, f is far from dictator. And we want it to be right. OK? So this is the problem we are interested in. Now let me tell you what is our definition for far from dictator. So our definition is going to be a little non-standard. It will be stronger than the usual definition. And to tell you what is far, I'll tell you what is close. And what is far is anything that is not close. Okay? So f is close to dictator if there is another function, g, from Rn to R, where g approximates f well in 2 norm.
What do you mean 2 norm? It's a real space. You mean Gaussian?
I have, yes, so I should say,
Gaussian measure.
when I wrote this, I meant with respect to the Gaussian measure. Thank you. OK. OK. So in the 2 norm, g approximates f. And g can be written, g of x can be written as a sum of coordinates among the n coordinates where there aren't too many coordinates. So maybe let's call it ij and j, where j is runs from 1 to something which is at most, say, 100 over delta squared. Okay, so this will be delta close, delta epsilon close. Okay, fine.
Close to linear Hund.
Yes, exactly. Okay.
Is this also equivalent to saying that you have a sparse representation in Hermite polynomials?
A sparse representation as what?
As Hermite polynomials?
So we really want linearity here.
Really want-
So only the Hermite polynomials, the linear Hermite polynomials should be significant. Okay, this is a very strong definition. What?
I think it's Hermit, but
Hermit. Okay. In Hebrew, it's definitely Hermit, but also in French. Okay.
Go fix the paper.
Okay. Okay. So require this strong linearity demand, and indeed, the first thing that we do is develop a linearity testing. Over reals.
It's like what you said before, like about your SDP algorithm. There's nothing special about 3, right? It also will work for 10 or something.
Yes.
Like that, right? So
Yes, but 3 is the minimal number where we can say something, and 2 is already something which looks essentially like the Unique Games Conjecture.
but in some sense,
SDP
already
works
10.
also for 2. So SDP.
The SDP works for any number, but 3 is the smallest number for which we can say we give an NP hardness result.
But is it much easier to give the NP hardness result for 10? Or
No, it's all the same.
so this-
Now we have the 3, right? So,
No, but it's
no,
not
you
like
just ask whether it could be easier. It could have been easier. Yeah. Anyway, we'll see.
okay. So linearity testing over reals. So let me just tell you what is the test. So we know linearity testing over GF2, and so yes, I should say you can take any function f and write it as a linear part plus a nonlinear part, where the linear part is really linear, is sum of ai xi, and the nonlinear part is orthogonal to the linear part. Okay, so in this sense, it may our problem is well defined. We want to ask whether the function is essentially dominated by the linear part, whether the nonlinear part is very small in 2 norm. Okay. Okay. So you can guess how linearity testing looks like. You pick Gaussian variables in R to the n. And essentially, what I want to do is exactly what we usually do, f of x plus f of y equals f of x plus y. The only problem is that x plus y is not Gaussian. So I have to normalize it. So it will be distributed as a Gaussian, and then I have to multiply here. Okay, but this is the test over reals.
So you again need to do some kind of folding. Oh no, you just said f is norm 1. That takes care of it.
F is of norm 1, yes, but okay.
By the way, this definition of linearity, f equals the linear part plus e. And why is this orthonormal to the?
That's the definition.
No, any function can be decomposed into a linear part and a non-linear part. This is
and the non-linear part is always.
And the non-linear part is always orthogonal, yeah.
With respect to the standard inner part.
With respect to the Gaussian inner
it's
product.
a projection, right, of the linear part into.
Yeah, you take it.
It's a subset.
Yeah, you take the function, you remove its projection on the linear part, and then you get.
So if you're thinking in terms of the standard Fourier representation, you get linear part, which is the singleton sets, and you get higher order ones. But the higher order ones are orthogonal to the linear ones.
Yeah.
So any combination of them is also.
So I should just think of it in the Fourier.
Yes.
Yeah, more.
Okay. So what we are able to show, and I won't show you, is that the 2 norm of the nonlinear part is bounded by the success of this test. Squared. Okay.
No constant.
There is some constant
Yeah,
here.
so it's
But,
essentially the same proof. Or the
So
very
it's
different.
not the same proof. So it's via Hermite analysis, which is the
It's completely
corresponding thing to Fourier analysis over Gaussian space. But so
But you cannot write you're in the Unique decoding regime. Can't you run the BLR?
no, it's a different case. So
Yeah,
in the Boolean Fourier analysis over GF2, you have the characters where the
No, I'm not suggesting. I'm suggesting BLR. Just if you do BLR, there is no characters of Fourier in the original BLR proof.
No, so yes,
No, but-
that's a good point, Avi. So I don't think.
yeah, we
So BLR will. I don't think BLR kind of works very well.
You tried. I mean, I'm just
Yeah,
asking.
we
I assume
talked
this was the
about
first
it,
thing you tried, because in the Unique decoding regime, you are allowed to lose a few, plus some error. I'm not sure it will work exactly in Juno, but I'm just asking. You tried.
yeah, we thought
Well, I guess
this
it
is
will
one of the
work,
first thoughts, but
Yeah,
No,
so-
no,
so
no.
One issue with BLR kind of analysis,
Yeah.
well, not that it's a problem with the BLR test itself, but quite often the BLR test is used. First, you show that the function is close to linear,
no.
and then it's usually used to make sure that if you want the value of this function at a point, you can get it by error correction.
Yes, the self-correction
So
doesn't
The
work
error
over
correction
real
just
space.
doesn't work over real space.
Yeah, I can show you
It
why.
doesn't work.
Yeah, this is
So that's
All right,
what
because
Yes.
it's never actually equal, right?
No,
No.
we don't care about equal. We don't
Okay.
care.
No,
You cannot. You
No,
just
no,
want
it's-
to
Okay.
estimation. So
okay. What is the
with
basic?
yeah.
What is the basic thing in BLR? And okay, so you want to get the value of x at the point x0. Okay, so what you do, you say this equals to x0 plus something which is random minus this thing which is random, and over discrete space, doesn't matter what this is. If this is Gaussian, then this will be Gaussian. This will be this will be random. This will be random, and we'll be able to do self-correction.
That's exactly the
So
difference.
they are no
What?
locally correctable.
Yeah. So the thing is that here, it will no longer be Gaussian.
Yeah, but still, the argument wants it.
The argument says that you can do self-correction,
Can't you do the same trick?
and you can't do
But
it.
anyway, what
The
does the thing
argument
that does
about-
work is this. So what you do use is the analog of Fourier analysis over the wheels.
We just expand it and we show that everything works. It's
And you're not in
Slightly
the unique
different.
case, right? You're in the list coding case?
yeah. We're showing this is not the unique decoding case. There will
I mean, if you,
we show that even if this is very small,
Oh, I see.
then you get
I
something.
mean, you're
or
doing the analog of
this is
Fourier,
very
which
yes.
works in the list
Yes.
coding.
No, but yeah, but
This is small.
if this is large, I mean, yes, if this is large, then you get something.
Even
You get
more.
something no matter what this
Yeah,
is.
No, but I don't think you use it. You don't.
What?
You use it. You use what happens. It's very loud.
No.
Or the-
No, yeah.
You
We
need
would
the
have been
decoding.
happy only with something like BLR. This is indeed something we tried.
Okay.
This is the major point, and this is actually was the barrier to proving the NP hardness result.
Yeah,
In the beginning, it's an
not a
important
unique,
observation.
Right? It's not a unique case, right?
No,
Yeah,
but
they
in our
prove
setting,
something, they prove something stronger. The question is whether it's needed later in the
Yeah, but
process.
even needed, isn't it needed, the
I
list
don't-
coding?
what?
I mean,
No, we don't
You
use
find
the
it
list
is
decoding
also
case. We
not
assume that
really
this is
the-
extremely small, and then we want to argue that this is also small,
But then
which is
but
the unique
gap's
decoding.
like really small versus almost one.
It's misleading. This is this, you would have been happier if this were like 10 to the minus 10 or something. Not if this is close to 1.
Or
You want to say that it's hard to even satisfy just very few equations. Here we're saying that it's hard to satisfy really lots of equations. Yeah.
But it's tight, so it's...
No, that part is not tight necessarily. No?
You could have, you could have like, you could conjecture that there is a result here of 10 to the minus 4 with some constant, appropriate constant here.
So is the low degree version of this also true? Can you do low degree testing?
We don't do low degree testing.
Did you think about it? The proof for low degree testing works over the reals?
I think all of those things over the reals, once you have degree D, you get like exponential in D. So it'll be probably more like a GF2 case.
What will it be exponential in?
Well, why? It's a large field.
Like
That's
all
not
these,
more.
no. All these error things over reals get an exponential in degree, kind of.
Anyway, maybe we want to.
Well, okay, so maybe...
Yeah, well... Yeah, I'm really... Yes, I should hurry.
Just one quick question. So the test, you test for equality or you test for approximate equality of this linearity?
I wrote it as equality, but everything here is approximate equality.
And in general, for your model, it's over reals, but...
And what we show here is that if this is small, then this will be small. So here we're actually giving a result on approximate.
So my question is, you work over reals, but in reality you work with some precision to a number of bits?
So right now I'm doing everything over the reals, like in an idealized setting. And of course, when we have to show construction, we have to discretize it somehow, and there are precision issues. But these are really negligible. Okay, good. Yeah, I should start doing things faster. I just want to say that the conclusion of all this is that if we do this test, we can essentially assume that the linear part is extremely small. Let's say that it is most 10 to the minus 10. Okay, and we can't get better bound, because maybe with probability 0.999 this will be really tiny, but with the remaining probability this may be large. So we can't get a non-constant bound on the nonlinear part, but we can have, depending on what is assurance here, we can have very low bound on the nonlinear part.
Generally, the way to simulate an end here, when you want to do like a test both linear and dictatorship, you just throw out half of the equations are devoted to the linear part, half of the equations are devoted to the and that's why you get something like 0.99.
This is one of the reasons, yeah. Okay, good. Fine. So okay, we have linearity testing. We want dictator testing. Right. It looks like we should be able to do it. We know so much about. Maybe I'll do it the other way around. Okay. We know so much about dictator tests and how to design them. Okay. Okay, so there is the standard dictator test. The first dictator test that comes to mind is this coordinate-wise perturbation test. So you want to check whether f is equals xi or is far from equaling xi for some I. Then what you can do is just pick a Gaussian x in R to the n, and then we can perturb it as follows. We'll get x in R to the n, where for every I, xi equals x tilde I will equal xi with probability 1 minus delta. and will equal some new yi, which will also be a Gaussian, new Gaussian with probability delta. Okay?
Yeah, actually, do it this way or just write xi tilde as 1 minus delta times xi plus square root delta?
No, I want to do it this way. We'll see other.
You raise a very good point. So what you said is a perturbation in a random direction.
Which
that
we'll see.
Will not work. This is a perturbation along
it's really important for us.
some set of coordinates. So if you write it your way,
okay.
it just will not work.
Okay.
We'll also see it shortly. Okay, no, but this test makes sense. We take all the x's, delta fraction of them essentially we flip. Most of them, 1 minus delta, we leave exactly the same, and so we can expect if f is a dictator, we expect f of x to equal f of x tilde with probability 1 minus delta. The value didn't change, and we get this. So this works well if we really get a dictator. The question is whether it works well when we get something far from dictator. Is this equation far from being true?
Even before, what do you get if it's close to dictator in the sense you define?
Well, so yeah, let's see everything. So no, but notice that we don't care. We don't care. We just care what happens if it's a dictator and what happens if it's far from dictator.
Now a linear function.
Oh, I have. Fine. I prepared this board first. Okay. Okay. So first, let's see what is going to happen to the linear part. So we can assume that the nonlinear part is extremely small. Let's see what happens if the linear part equals some linear form, but a form that depends on lots and lots of coordinates. Now, to simplify things, and this is a simplification that is just for the presentation. It's completely meaningless, and you can do everything without it. Let's assume that all the AIs are the same. So this is, let's say, IJ, AJ, IJ, J runs from 1 to K. All the all the AJs are the same and equal 1 over square root K. Okay. And K is large. So it's larger than 100 over square root delta. Okay? In general, we can have different coefficients, but the same analysis will essentially carry through. Okay, so let's see what's the difference between x, the value on x, and the value on x tilde, at least with the linear part. So I just substitute what I have here. Most of the coordinates remain the same. What I have here is only the coordinates that change. It's about delta fraction. So I have those x, whatever, xi, xl1 minus yl1 plus for something which is with high probability. So I have those delta k summits. And this is all with a normalization of of 1 over square root k. Okay. So this is the linear part. All those things are just independent Gaussians. So I have here just the sum of 2 delta k, around 2 delta k independent Gaussians. This is going to be, with probability, say, 20%, this is going to be the sum is at least, say, 0.4 square root delta. This is just the sum of many Gaussian variables where I assumed that there are enough so I can apply some Chernoff here or whatever. Good. So this seems. What? When this is. You want it. Very good. Yeah. When this is large, this is far from being a dictator, and I want it to be large. So it looks like we're essentially done. We showed that this difference is going to be the sum, at least in absolute value, is going to be large with a nice probability. But here I only referred to the linear part, and the question is, what happens to the function, not just what happens to the linear part. Okay, let's continue here. So my equation was f of x minus f of x tilde equals 0, which equals what happens in the linear part, but also with the interference of the nonlinear part. And we know that this is large, but then it's not clear that the overall sum is going to be like
much smaller than 10 to the minus 10.
Yes, and the reason is that we know that this is going to be very small in general, but this is very small, which is constant, not very small delta, and it can easily interfere with this square root delta and completely eliminate it. Okay. So perhaps this test, which is the natural test you would try, does not work. Okay, so let me just record like on the board here. What happens if this does not hold? If the test does not work? It means that we know that with probability essentially 0.2, we have that the difference between the value of E on X and on X perturbed is large, which would be around 0.4 square root delta. Okay? For this to be essentially 0, when this is very large, it means that this should be very large. Okay? And we know that this is very large often. Okay, so let's put this aside, and let's try to remedy the situation. So we somehow have to say that when perturbing X, the value of E cannot change too much. And at least in some setting, we are able to show this. So this will also bring us to something along the lines of Bose's remark. And this will be the random perturbation test. Okay. So what we can do is say the following.
So you're describing a new test.
I'm describing a new test.
Yeah, you had the coordinate-wise perturbation.
And now I'm talking about a random perturbation test.
But you are going to perform all of them, like, so you're going to perform, like, with probability S3 the linearity test, with probability S3
yes, exactly.
and then with probability S3 this one.
Yes. Maybe I will say that this is when x and x tilde are taken from this coordinate-wise. Perturbation distribution. Okay. Okay, so now we can look at a different distribution where we pick x, Gaussian x, now to the n, and we'll pick also a y as before. But now we'll define the perturbed version of x to be 1 minus delta. Will be this variable with correlation 1 minus delta with x. With correlation 1 minus delta with x, with coefficient 1 minus delta, it's x. And then with the remaining coefficient, it's going to be just 2 to the delta. So I need the square of this plus the square of this to be 1 if I want this to be Gaussian, right? So this is this. This will be 1 minus delta correlated version of x. Let's call this, so I won't have to write it the time. This will be lambda 1 and this will be lambda 2. And now what I can enforce is that f of x tilde equals 1 minus delta f of x. So it's essentially the same as f of x plus this lambda 2 y, f of y. Okay, so this is just by linearity. Any f that is linear, in particular the dictators are linear, will satisfy this. And this shows that the function, the value of the function on the perturbation is essentially the same as the value of the function on x. Okay? Now, I want to remark that one may object to this equation, saying that we have some coefficient here which is extremely small. And then sort of what is the point in measuring the contribution of this to the norm when actually this variable doesn't matter too much or things like this. There is a way to change this equation into an equation where all the coefficients are of conformal norm.
So what is one might object? The question is whether you do this or this is useless and you do something else which is useful.
So our theorem, so if I don't say anything, our theorem says that not only there is a system of equations, there is also a system of equations where the coefficients are essentially of the same magnitude. And if you want to do this, and this is what we really guarantee, you have to change this.
Why is it important to guarantee that?
Because you can say that it's sort of not the right, it's sort of almost meaningless if you have some coefficients that are extremely small, that they make this variable.
Makes it closer to a tooling. That's only better. Like since it should only make the problem. Why is it made it?
Okay, so it's more or less for aesthetic purposes. It's just nice to have all the have some guarantee on the coefficients that you don't do something fishy by having small coefficients. It's more.
So they are all absolute constants. In the you can get them all to be absolute constants.
Yeah, all of them will be let's say between half and 2.
There is intuition why this could make the problem harder and not easier by making very small coefficients.
No, so we were also thinking of potential reduction from 3-lin to 2-lin. And somehow for that it was nicer to have some control over coefficients and such things. But now that we don't have that reduction, we are not going to tell what the reduction is. It's more or less for aesthetic purposes.
Wait,
okay,
so
you can just ignore this discussion. It's what?
You can
All the
coefficients are of the same
say
magnitude.
between half and 2.
But this is not the part that costs you blow up of 1 over delta?
No, of course not. The blow up of 1 over delta is inherent and... Okay, just, ignore this remark. Suppose that this is our equation, okay? It's an equation that the dictator function definitely satisfies. And what it says is that the function is going to be very close, even if you perturb. Okay, so let's do it. Suppose that this equation holds. This equation definitely holds for the linear part, right? So if this holds for the function, it holds for the linear part, it means that it also holds for the nonlinear part. Okay. Now recall that we know that the e's are extremely small, are some very small constants with high probability because we have this bound on the norm of E. Okay, so with high probability, we get that this thing is some 10 to the minus 4 square root delta. Okay, because this is of the magnitude of square root delta. This is going to be a very small constant with high probability.
Wait, where did that come from? Oh.
We have a bound on E, on the norm of E. The norm of E, the total norm, the 2 norm is 10 to the minus 10 because of the linearity testing. Okay? So this with high probability, the E part is going to be a very small constant. This is about square root delta. So we have, with high probability, this is going to be small. Okay. And we have that essentially the difference between those, between this and this, is going to be of the magnitude of just square root delta times a very small constant. Okay, so let me write this here. If I take x and x tilde from the random perturbation test, well, random perturbation of one another with probability at least 0.9999 whatever, E of x minus E of x tilde is at most some 10 to the minus 4. Say, what? Square root delta, yeah, I wanted 10 to the minus 4. Okay? Okay, so we have some, so this is not an equation, but an approximate equation with some deviations like this, and this is this, and maybe here we have another delta. But this is all bounded by some very small constant times square root delta. Okay? So far, there is no contradiction. But let me tell you why those things. It seems fishy that they will coexist. So why the first evidence that it's fishy is that in general, so we have here 2 ways to perturb an x. One way is that coordinate-wise, you leave almost all the coordinates the same, just delta fraction you change. The other is you basically change all coordinates by some square root delta deviation, shift. Okay. So it seems that changing all coordinates makes you like mix faster, makes you the value should change more than if you essentially stay the same. Okay, and what I can prove is that on average, when I take x of x prime from the random perturbation, the change squared is only going to be larger than the change if I perturb coordinate-wise.
That's true for any function?
This is true for any function E.
Any function, not necessarily orthogonal to linear.
For any function E,
so
which is...
how the examples here should be the functions that are like farthest away from a dictator, right? Like that.
So what's the lemma? Is that finished? So
it's finished now, yeah.
What are the two distributions?
Here it's the random perturbation, and this is coordinate-wise perturbation. And what we're saying is that amortized on average, if we change, by changing all coordinates a little, we change more than if changing just very few coordinates. Okay. Fine. I think that, wait, Buzz, did you want to?
So I want to answer if E was a dictator, what would be, and this was delta, the parameter delta. So the bottom, the right-hand side of the inequality would be delta, and because that's the probability you're going to change, and the left-hand side would be?
The left-hand side, the upper. So now you change xi moves to xi plus square root delta yi. Okay? So the difference
the one coordinate is the same shape.
is this.
It'll be equal.
So it will be equal. So in the coordinate in the dictatorship it will be equal, and you're saying it's for any function.
And for any function, if you change all coordinates, you change faster than if you change just very few coordinates.
I mean, if you change like something like delta over 2 or delta over 10 coordinates, I mean, if you look at delta over 10 coordinates, the two perturbations are the same. If you look at only a small fraction of coordinates.
I look at only a small fraction of coordinates.
No, I'm saying.
Oh, just restrict my.
Yeah, the two perturbations are the same.
Not exactly, because here
no,
I change delta fraction, I change completely, and here I change everything.
The proof is a hybrid argument?
No, the proof is by Hermite analysis. Maybe there are other proofs for this, but I know a proof with Hermite analysis.
Why don't you use the second distribution in the first test now?
I can't do. This is the only equation that I know. What do you ask, actually?
So you have two distributions.
Yes.
One called coordinate and one called random.
Yeah, but I can't do this test for the random. For the random, this is the only equation that holds.
No, so the random test is essentially again a linearity test. So again, linear functions are going to pass it. But you still want to rule out functions which are linear but spread out.
So why don't you use in the first test the second distribution?
Because you can't. You don't have a meaningful. You don't have something that the dictator test will pass with the second distribution. What? If you change all the coordinates, then even if you have dictator, you change it by. You change it somehow. You can't say that the values will be the same.
So it's for the completeness, right?
For the completeness sake, yeah, exactly. Okay, so we can have a short break now. Yes. Okay, so let's have like a 5-minute break, and I'll prove it to you afterwards. Okay. S times Fourier coefficient squared. Yeah, so I should tell you what is the meaning of all those Fourier coefficients and Hermite analysis in Gaussian space. So in the discrete cube, we can say that we take the function and then we write it as a polynomial, and in the discrete cube, x squared equals x. So we basically don't need degrees higher than 1. So we can write each function as a multivariate polynomial. Over real space, of course, we can't expect to do anything like this, but we can write each function or approximate each function arbitrarily well by a polynomial. And the Hermite coefficients correspond to the coefficients of this monomial. Each monomial is indexed by this S, where the S says, what is the monomial? What are the degrees of each of the coordinates that participate there? So this is the S here, and when I write the size of S, I mean the sum of the degrees, the degree of the monomial. Okay.
And that's exactly the difference. If it was multilinear, these two would be exactly equal.
Yes, that's true. Okay.
In the cube, they are the same distribution, but
Yeah.
But
One of them it will be sum of the degrees, and the other it will be number of terms, I suppose.
Okay. Fine. So I have that the.
So maybe S is like not necessarily like it's really the degree of S.
The degree of the monomial, yeah.
Right. And then, like Madhu says, on the other hand, it will be like this size.
Yes. Okay. Okay. So this is exactly twice. What?
This is with C.
What?
I don't understand why you do it for the multivariate case.
I'm not doing it for the multivariate.
What? Why do?
Yes, you could do it for the.
One variable is as good as all of them.
Yes, but it doesn't cost me anything to do it for the multivariate case.
Well, there are subsets. So
There are subsets, yeah.
maybe you should call it hybrid idea.
I mean,
Because it's
in this
But
notation,
anyway,
it doesn't really matter.
it doesn't really matter. Okay.
Anyway, I mean, so now you're doing the other distribution, the C, right?
No, I'm still.
Let me just,
Why?
I just want to.
let me just say something. I hope this is true. A, that the multivariate case reduces to the univariate case because by
It's
hybrid.
all, multiplicative.
Yeah, you prove it by sequence of inequality, by hybrid. And the other thing is that for univariate case, it's just that the first one has bigger variance. Right? You have two distributions, variance, right? And that's what
First
you're
one has-
measuring in the you have two distributions, one with a bigger variance, and that's what you're measuring in this difference of square, right?
Yes.
The variance. So
No, yeah,
one
but
distribution-
why the first?
Oh, why you can calculate the
You can
variance of the two distributions? Let's see,
Yeah.
but that's in some sense what you're.
This is what we are doing. Yes, that's
okay,
true.
so at least I understand why it's true. So that's
Okay.
I mean, I think if Avi is right, then probably it's a simpler proof. I mean, in the one variable case, there is no reason to use Fourier or anything. But
Probably, I think even the one variable case, again, you are going to expand it with the Hermite expansion and do the same thing. So the point is, you might as well do it for multivariables, and it really doesn't cost you anything.
Unique expansion of the one variable function.
Yeah.
Cost you more subscript.
Okay. Fine.
But we just need to compare the two things. Like this calculation is true for the C and the R, right? So you just need to show that when you choose them according to R, it's
Yeah,
less
but here I use the fact that I'm considering the R, and I don't know how to.
okay.
Okay. So this
with
is
the R.
this was the calculation for the R case, for the C case. fine. It's also an easy calculation. So what do we have here? So we pick some subset of the coordinates by each coordinate is in the subset with probability delta and not in the subset with probability 1 minus delta. And then we fix everything outside of the subset. They are the same for x and x perturbed. And then we take the two different choices on the subset and look at the difference. Okay. Good. Fine. So let's write this. So this is 2. So this is the same as the variance up to factor 2. So and the variance when I change what I do on this subset, the changes of if x. Good. Now, well, you can use influences of sets over functions, or you can just expand it. You see that this is twice the expectation over the sum of all s's, where the intersection with these non-empty of es squared. Okay. Fine. Which is the same as to count every subset, every monomial S, to count it with weight, which is proportional to the probability that the intersection is not empty. Okay. Fine, I'll write this here. So the probability over D that S intersect D is not empty. So this is exactly, the probability that it is empty is the probability that I miss every coordinate that is in the support of S, which is at most S delta. Okay. No, this is fine. The support is smaller than the size.
And 1 minus delta is
No, it's great.
And the not empty is 1 minus, and therefore what?
The do is right. The support is smaller.
Support
than
is
S.
greater.
The
You want
support-
it greater, so it's greater.
the
and
support
you want
is-
it to be greater.
Okay,
Because
fine.
later you-
That's true. The support is smaller than the size, and
Great.
okay, good. Thank you.
This and then it works.
Okay. Good. Okay, so we have that inequality.
So you don't, it's not what was said, you don't need to do both the random and the coordinate test. You just need the coordinate test. You just show that it will be small.
No, but the coordinate test, I can't show that the equations will be falsified with a large margin. This is what I.
So I think this is what follows from
The
the.
No,
lemma
no.
doesn't say
No.
anything if the coordinate test is small. It says something if it's large.
What?
Isn't the conclusion of what you just did that?
Right now there is no
whatever-
conclusion. Why? Let's see. Why there is no conclusion? So, what bothered me is that maybe those two happen simultaneously, and then I can't say anything. But this does not forbid those two to happen simultaneously, because this talks about the average. And maybe with probability 0.999, this difference is going to be extremely small, but then with the remaining probability, maybe it will be large. So we have this, which is some constant, and it completely does not contradict the first line. Okay, so we'll have this, which will be 0.00001, and we'll have the random, the coordinate-wise, or this, and we'll have the coordinate-wise perturbation, which is with some constant probability square root delta. It's much smaller. Okay, so right now we're not done. This is exactly what I now have less than 20 minutes to show you why we actually are done, why those two cannot coexist. And let me tell you what is the idea. The idea is that instead of considering E, we'll transform E into a Boolean function. Okay, so what we'll have is that, so the difference will be here is at least 0 square root delta. We'll make sure with Boolean functions the difference is either like if they are changed, if they are different, then the difference is at least 1. Okay, and we'll make sure that usually in this case we actually have difference 1. So overall, this will be a large constant, and here we'll make sure that usually these two will have the same value, and this will be mostly 0. Okay, and we won't have the problem that we had before. Okay. So this is the plan to convert E into a Boolean E, where if it changes a lot, and if it doesn't change, it doesn't change at all. And then these will be contradictory to this.
Can I ask just one thing about this? What is the support actually in the?
So each S is a monomial. Each S corresponds to a monomial in the representation of the function as a polynomial.
The degrees, yeah.
And the support is which coordinates appear in the monomial. Okay, and this is as opposed to the degree. Yeah.
Okay.
Okay. So any questions? Okay.
So this is just to convert, what you're doing now is to convert this average. You really want this average statement to become a high probability statement.
I think about it the other way around. I leave this statement holds as is. I'm just changing the is, so I'm given things that are strong enough to contradict this.
So maybe another way to say is that suppose the lemma holds with, instead of the squares, suppose it holds with absolute values. Suppose hypothetically, then whatever is written on the upper board directly contradicts the lemma, right?
Yeah.
So
wait,
yes.
No.
Yeah.
Yeah.
No. If here I have absolute values.
Yeah. If you had absolute values, then.
No. Maybe here with probability 0.0001, I have some constant.
Okay. Yeah.
Right. This is the problem.
Yeah. It still doesn't. I mean, E needs to be bounded and such things.
No, it's bounded, but it's bounded by a small constant and not.
Or maybe if E was Boolean function, 0-1 valued function.
Yeah, if E is a 0 valued function, then whenever there is a change, there is a noticeable change. There is not just a square root delta change. And this is exactly what we'll have, and then what I said before is not going to work. And it will contradict this. Okay.
I'm just in the same direction. Can you prove the lemma for higher moments?
So the Hermite analysis thing does not work for higher moments, right? I don't know. I don't know. But this will be enough because I'm going to convert E to a Boolean E, and then change will be noticeable change.
So now
This will be a contradiction.
If it's a Boolean E, then this lemma is not just an expectation. You just measure the measure of the places where these two things differ.
Yes. Yes.
Yes,
that's true.
Right. So now.
Yeah.
So if you want, you can say when you make it a Boolean that you really change the conclusions of the lemma.
Okay. Okay.
How much do you lose in changing this E to Boolean? Like, do you lose anything in your equations or the way you do your test? Or
What was the? How much I lose in the parameters, or how much I lose what?
in the parameters or the way you write the test?
The tests are exactly what I told you.
Okay.
This is just the analysis. I'm just going to show that those two facts cannot coexist because they will contradict this.
Maybe we can finish.
Okay. So, fine. So let's see how we do this. So let us represent whatever information we have on those perturbations in a graph. So let's define perturbation graphs. Where the vertices will be the points in R to the n. And we're going to have two types of edges. We're going to have, let's do it with red, C edges. And we're going to have R edges. So the C edges are between x and x perturbed, where the weight of the edge is the probability of those two to occur when I choose from C. And I'm going to connect, so it's comfortable for me, I'll connect only x's where the function is really small. So let's say that it's smaller than half in absolute value. So recall that that my E is extremely E is extremely small. The norm on E is extremely small. So with very high probability, this is going to hold, and I haven't changed anything. And we'll also require that what happened is what I'm promised usually happens for the C, which is the difference is at least this 0.4 square root delta. Okay. So I have those C edges. I also define R edges. So this will again be x and x perturbed, where the weight is the R probability. And really I have this condition that is at most is 10 to the minus 4 square root delta. And those two are bounded. Okay. So now I have those two graphs where I have the blue edges and I have the red edges. Okay, good. A Boolean function on Rn now just corresponds to a cut. Any Boolean function is some cut in the graph. Okay? And I'm looking for a cut that usually cuts the C edges and mostly doesn't cut the R edges. Okay. Okay. So let's do it.
You mean in weight, the weight? So you're talking about the weight of the cut. It seems that there are many more R edges, right? Because the values are smaller.
There are many more.
According to your calculation, you say that for the particular E that 10% of the edges are going to be both red and blue, right?
So edges mostly won't be both red and blue, just because.
Because the weight is higher, and the total weight is higher. The difference.
First of all, they're essentially on different pairs, right? The red and the blue, because coordinate-wise perturbation doesn't look like random perturbation. Just different pairs are there, and yes, I will have lots of what is it? Blue edges. Blue is what? The R probability.
The total weight is bigger, and each individual is small.
Yes. Okay. Fine. Okay. So the first claim.
Something geometric will cut more red, like a ball will cut more red edges than blue edges, right?
Because of the geometry of the red edges, or what?
Because the red edges are, because the random are, the points that are connected are closer to each other.
No, I'm exactly going to use the fact that things are closer to define the cut. Okay.
Wait, I thought they are rescaled so that the expected distance is the same because of perturbation. No?
What?
That if you take the red perturbation versus the green perturbation, the two, that the expected displacement is the same. No?
What is displacement? What is expected displacement?
Like x and x tilde.
The distance is the same.
The distance is the same.
So I don't understand.
No, because otherwise you are comparing apples with oranges.
Oh, the x and x tilde. Yeah, that's true.
So then I don't understand how.
Anyway, maybe we can see the proof.
No.
But what you're trying to show that this is this cannot simultaneously exist.
Yes.
Right? That
I'll show that if this exists for E, then I can construct from E a new function, E prime, which will be Boolean, and will essentially satisfy similar properties, but for Boolean, it will already be a contradiction. Okay? Okay, so how do I define this Boolean function, or equivalently a cut on this graph? So the first observation is that there is a distribution over cuts where each C edge is cut with probability. So C where at least 0.4 square root delta, and each R edge is cut with probability at most 10 to the minus 4 square root delta. Okay, so does anyone see how to prove this? yeah. So I can just, so I know that all my EXs are between -half and half. Everything falls here. And I know that the red edges are far apart. The blue edges are close. So if I just pick a random threshold and put everything here from one side and everything here from the other side, then the probability it crosses a red pair is this. The probability it crosses a blue pair is this. Okay? So this is fine. But this is not what I wanted. What?
Why doesn't it like complete the proof?
Because we didn't do anything. My problem was that the expected difference in the first case, in that board, here it was something of the order of square root delta. And the square root delta can be beat by this 0.0001 probability here.
Expectation of this distribution of the number of C edges cut divided by the number.
No. The problem is that besides the edges on the graph, I also have this 0.00001 edges from here that can completely change. Then can completely beat any change which is just square root delta. I need a change which is, of constant fraction for this to be a contradiction.
But this is not 0.4 delta. You have to multiply this by 0.2 for the probability, right? You just get for this.
No, I'm just saying. No, this is just about the graph.
Maybe there's some constants.
It's about the graph, but in the graph, only with probability 0.2 do you get 0.4 delta jump.
No, here I just said each edge, I fix an edge, and I'm saying what is the probability it is cut. The probability it is cut is exactly
but only
per edge. This is accurate. Okay. Fine. The second claim that will finish everything. Almost finish everything. Is that there is a distribution of our cuts where each C edge is cut with probability at least more than 0.3, and each R edge is cut with probability at most 2 times 10 to the minus 4. Okay? Fine. And I think now that you have this, you can really deduce that there is a cut that contradicts these two. I hesitate whether. Okay, I'll definitely show you the proof of this claim. Let's leave it here. Okay, so here is the proof. Don't pick just one cut, but pick lots of cuts. Equals 1 over 0.4 square root delta. Cuts from the previous distribution. So I have C1 to Cn. Now, for the sake of analysis, we'll just take half of those cuts. So pick I M by taking each I y with probability f independently. And now the new cut, what it's going to be to do for point x is just to take the XOR of all the cuts in I, all the cuts that I chose. Okay. So what does it mean? It means that if I have an edge, maybe I'll just say the rest of the argument. If I just have an edge that is not likely to be cut at all, like an edge, like an R edge, then no matter what, I'm not likely to cut it here. I don't choose so many cuts.
You could have taken the O the same, would be the same now. I mean, you
So
just would distinguish 0 and 1 really in this.
So if I take an OR,
you just, I mean, with the probability,
then this will still hold.
You either the XOR distinguishes for you 0, you know, that you didn't cut at all from cutting 1. That this number of cuts either cut nothing or cut 1.
Yeah.
Right? That's what you eventually do. So it would have been the
But
OR.
you're looking at the function on not at the edges, on vertices. So
Yeah.
I mean, if you take the OR, it will be a very, very unbalanced cut.
What do you care?
So somehow it's, I doubt that it could cut a constant function of the vertice. You can cut a constant function of the edges if your cut is like if your cut takes only a tiny function of the vertices.
No, but I think that you're right. I think that OR will work just as well. The R edge.
OR probably will not work, right? Because then you're somehow giving logical values to 0 or 1, and then OR is
the R edges are not going to be cut at all.
I mean, OR will take a huge, will have a cut with
and
that
the
has
C
a tiny
edges
side and a huge side, and that a cut like that cannot cut a constant function of the edges.
Yeah, that's one thing.
No, but what
I
won't
don't
work?
understand
No,
No, the
not
point
a
is
tiny
that-
side
Well,
and a
she
huge
still
side.
didn't complete
In
the
fact,
proof.
the balance of the two cuts will be
No,
different.
the proof is that an R edge is not with, high probability is not going to be cut at all, and then will not be cut here. While a C edge, it will be cut at least once here with some constant probability, and then with probability half, it will be cut here, right? So it looks like the OR should work. No?
It cannot. It will be like very, very big, and one side will be very, very small. And you can only cut 10%, 30% of the R edges if you have a cut that's roughly balanced.
No, but the side is something like 1 minus the square root delta to the m. And m is about
Yes,
1
but
over
this
square
is
root.
delta
This
is
is a constant.
no delta is
No,
extremely
each cut
small.
is like, as far as we know, is like half-half, right? It's each side, like, you take cut from the distribution, it's probably like half-half.
No, in the OR, sir. In the OR.
So in the OR, when you're doing an OR, it's like one of the sides will have like sub-constant size.
I think it will be a small.
So what? I don't see why it doesn't
In
work.
a regular graph, if you take
It's not
a
regular.
cut,
I mean, it's just it's something satisfies this distribution. We don't know what the graph looks like. We don't know what the graph looks like. We just have these abstract properties that it's, the initial distribution.
So suppose you took OR, then let's say the first cut